Hello, welcome back to another video log recording session where I talk about genetic algorithms, the very basic stuff, and I hope I can get to more advanced concepts and practices in the future. But let's see where all this leads to. So. Unfortunately, this is the second recording of the same Jupyter notebook that I'm doing tonight. The date is 2025 March 8th. Yeah, because this notebook is well, the things in this notebook are quite long, or kind of computation intensive in terms of computation. I won't actually be running any notebook cells while recording, so I'll just be going over the results that I got on my MacBook Pro, because Google Colab, the basic computing environment that Google Colab provides, is 3 to 4 times slower than my laptop. So here we go. This notebook, named Genetic Algorithm Grid Search 3, 30 items, was created to assess the impact that length of genome has on the evolution and the effectiveness of solution generation. Again, and almost always again, with population of null entities that contain nothing to begin with, or what I usually call void genes. So the first few, most of the cells here are almost the same, except the well, for example, this import stuff, the very few cells that the very few lines, these lines that I use to import the things I need, it's the same. However, some changes have been made to the items list, the utility values list, and the constraints list. 10 items have been added, namely keyring, A4 papers, a pack of A4 papers, A4 sheets rather, a straw, a battery, a tumbler, a wipe, as in for your glasses or your mobile phone, and a lottery ticket, and some cash, a camera, and a cap, as in a baseball cap. And accordingly, 10 additional utility values have been added that correspond with the newly added items: 40, 50, 20, 30, 15, 10, 15, 25, 20 for all these new values. And 10 new constraint values, or physical weight values, have also been added. 50, 400 being for the group of A4 sheets, like an envelope of A4 papers. And so 50, 400, 10, 100, 300, 5, 5, 10, 350, 150. So, and therefore the total sum of all the physical weights or constraints are 6805, and to account for the newly added items and the total newly calculated total sum of physical weights, the hyperparameter, all these functions are the same. Nothing has been changed there. However, the hyperparameters have been changed. Now that the total sum of constraints is 6805, We can see if that's correct. Yep, 6,805. The hyperparameters have been, again, arbitrarily adjusted to 5,000. Population size is still 500. Number of items is now 30. So is the genome length. The mutation rate is 0.03 or 3%. Crossover rate, although I don't use it, is still at 0.7. Generations is 10, but this value will change to however I need, or it could change. So once I've adjusted all these changes, I use them to initiate genesis and play and commence evolution. See, again, void genes that are 30 elements long have been created, and multiply them by 500. Yeah, that's one thing. I'm not sure if this is going to actually matter. If yes, I might have to. Yeah, I don't know. Maybe I might have to do a total redo over. Just to, I'll have to make sure this is the right way to do it, so that the changes don't get replicated across all the lists within the list. So, yeah. I mean, it could, but. Okay, so we start the evolution for different numbers of generations, ranging from 50 to all the way to 3,000. In total, that's 91,500 generations. And again, as I said, I'm not going to run this on Colab, and I'm not going to run this on Colab, but here's the result. The average of top 20 and 30 entities were recorded in the as results in terms of their summed utility values. Each summed utility values of each individual entity. And here is the plot. This is exactly the same behavior as we have seen last time, when there were only 20 entities, 20 elements in the genome, 20 items. So nothing unusual there. So the second step would be to evolve for the same number of generations, but 5 times. And yeah, 5 times. So I do this for 3,000 generations, and save everything in the result list. And when I do this for 5 times, I calculate the average of top 30 entities again and plot them. So this is what happened. So nothing that much unusual here either. So we move on. I mean, nothing that much unusual compared to what we've seen when there were only 20 items, 20 elements in the genome, in the entity. So next up is we evolve for once, but for very long, for 30,000 generations, and then see what happens. And then here's what happened. It still oscillates, so nothing really unusual there. So it goes up and then goes down, goes up and then goes down, etc. But bear in mind, this is still, this is still, is that the right way to say that? Bear in mind, just keep in mind that this is still at every 50 generations or 50 steps. At every 50 generations. So there's nothing unusual. So now we would want to see the progress or the lack thereof at every generation. So we record at every generation but evolve it for 10 times for 3,000 generations. And when you plot it, this is what you get. And then now we start seeing something quite unusual. Or there have been cases like this where there's a spike and then we don't see the spike anymore. We don't see a spike as high as this anymore, or as anywhere as close to this anymore. So that's weird. But we zoom in and then plot everything until generation 150, and here's what I mentioned. If you look at the red squiggly line, it peaked here and then it goes down, kind of comes back up again, and then it goes down, and then it starts plateauing all the way there. And so do the other lines as well. So that's kind of weird, but let's move on and generate 10 times, evolve for 10 times for 3,000 generations, but for different numbers of generations, ranging from 10 entities in a population to 2,000 entities in a population. And when I do that, this is the graph, this is the plot, and this is kind of exactly the same. But when we have a look at it, like here, plotted until generation 300, we start seeing the peak, and then it goes down, only to never come back up. And then 500, until generation 500, this red, as shown in this red line, it doesn't come back up. Only this brown line kind of stays there. But there is a general trend that's sort of going down. So there is a peak, and then there's a slight bit of a fall, and then it starts plateauing out and never reaches the peak again. So, and I just this could be nothing, or this could be something, but as I've always said, I've done more things after this notebook. I just know that something is up. Spoiler alert. So when I see a peak and a plateau that is at a level that is somewhat lower than the peak, I would say that a dip exists. DIP exists, and my concern would be, or my next curiosity would be, how to eliminate or minimize or control the dip. Because if you think about it, like this, think about it. If you don't know what the best solution, what the best entity is, because the problem set has some very complex definition or complex situations, and it's not really clear cut. It's like a knapsack problem. But yeah, so it's almost impossible for us to know what the best one is. But it would be a shame if we evolve a population for more than 500, 1,000 or 5,000 generations to somehow for it to come up with near perfect solutions, near perfect entities. It would be a shame if we keep losing what were potentially better ones in that context. Not every time, but in that context. And furthermore, it would be quite satisfying, and it's very intriguing. It is very intriguing, and it will be quite satisfying to know what the best practice is to ensure that the evolution doesn't lose data or doesn't lose information, or rather, it can, but it can always generate it back. It can always recover it back somehow through procreation and mutation. It would be so much beneficial for us to know what the generally practical and viable technique or methods of doing this is, rather than knowing what the answer is and then stopping right there, because that also beats the purpose. If you know what the answer is, or if you know what the best answers are, close to what the near best answers are already, why bother do this? That beats the purpose. So the beauty is in not knowing, but the bigger beauty, the more valuable beauty, is in ensuring that the evolution techniques and the process or processes and the methods ensure that the peak comes and then the peak becomes the plateau, that and that the dip actually kind of never occurs, or even if it occurs, it bounces back up, or so in other words, just minimize the dip or eliminate the dip. See, I don't know if the dip seems bad for now, but I'm not really sure if that's actually bad. What is bad is never recovering after the dip. That's bad. Never recovering to the level of peak after the dip. That's bad. The dip itself, I don't think is necessarily bad, but never regaining or never coming back up to the level as it used to be, as things used to be at the peak, that's definitely bad, because it means something is hindering the process, hindering the progress. Yeah. And that's it for this notebook. But the next notebook that I'll be doing the video log on will be with 40 items, and the one after that will be 50 items. So those were like spoilers, but yeah. Thank you for watching. Goodbye.